And last one to make a presentation. I'm from Germany. I make my PhD study in the Technische Universitat Chemnitz and take the performance improvement of the virtual machine as my research topic. I'd like to present a part of my research work here. During the past years, I encountered some common problems for the performance loss of the virtual machine, which are typical for all kinds of virtual platforms. So I attempted to address, to find the potential performance bottlenecks and work out the solution to this problem. First, I put it like this, a little bit about the concept and the impression of the virtual machine and its performance. Then I'd like to come to our major concern of the performance studies, namely the memory paging. We focused on the shadow and nested paging, which are the two popular web paging methods for the virtual guest. Then we studied we categorized the workloads by their behavior in memory access. And then we combined the two mechanisms together to get the maximum benefit of the two mechanisms. Then we analyzed the problem and designed and implemented the part of this problem. And we take the TASEC benchmark as our tool to measure the performance of the two paging mechanism, and finally the contribution and further work. What is the virtual machine? The virtual machine is actually a layer of software which performs the functions of the underlying hardware. The person, Portek and Gon, which is famous for their study in virtual machine, make a very short, brief summary of the characters and efficient, isolated, duplicated of real machine. And as many other things, virtual machine also has its benefits and drawbacks. Now we only focus on the drawback, namely the performance overhead of it. And the right figure depicts a general impression of the performance of the TASEC benchmark suite. We notice that for most of their applications, they perform at nearly a bare metal speed, but with several exceptions, which suffers the significantly performance overhead. So what is the reason for this performance loss? After a series of benchmarks, we have finally come to the conclusion that the memory paging method is key to this problem. Here we present we configure the virtual machine with shadow page table and nested page table respectively, with different page size, with normal page size of 4 kilobytes and the huge page size with 2 megabytes. we can see that the most applications, the nested page table can have again a significant performance boost against the shadow page table. And the below plot depicts the performance of the shadow page table and nested page table with a huge page. We observe that the huge page has a better effect for the nested page table than the shadow page table. So we naturally come to the idea to combine the advantages of the two mechanisms. Now we take a close look at the memory paging mechanisms in the non-virtualized and virtualized cases separately. The first depicts the paging mechanisms for a non-virtualized case. We can see that the virtual address is translated by the page table to the physical address. And in the virtual case, things are much more complicated. There are two levels of address translation. On the above part is the normal virtual guest virtual address translated by the guest page table to the guest physical page address, and then it was further translated to the host physical address by several other mechanisms, which we will address here in detail. Now let's look at the one mechanism in the virtual machine address translation. The first is the shadow page table. We can see that this is the guest page table maintained by the guest operating systems, and the below part is the shadow page table maintained by the virtual machine monitor or the hypervisor. And now this mechanism has the benefit is that hardware independent and low requirement for the hardware support of memory virtualization. But the drawback is very complex in its software implementation, so it increases the code base of virtualization software. And more importantly, more worse is that it triggers the page fault in the where guest triggers exit to the host kernel and suffers large performance loss for a certain kind of workload. Now let's look at another mechanism, which is firstly considered to be a replacement of the shadow page table. And this is the normal guest page table, but with this, only with this page address cannot be translated to the host physical address. Only with the help of the nested page table can it be possible. But so in this mechanism, it never triggers the page fault, never triggers the VM exit. So large part of the performance loss is avoided. But meanwhile, it introduced new forms of overhead by the two-dimensional page table working. Each page address translation is nested by the page table walking from the guest physical address to the host physical address. But as a compensation, people use the TLB hardware address page table TLB to avoid the very expensive two-dimensional page table walking. And this mechanism is very effective. But in some cases, the TLB suffers great miss. So when the TLB missed the page table, the two-dimensional page table must be walked to look the desired address. So the advantage is handled by the physical processor and no VMEZ trigger due to the page fault. More efficient for most of the workloads. The drawback is new overhead introduced by the TDP, two-dimensional page table walking, and in some cases it still yields poor performance. Then, depending on specific hardware features for virtualization support, which sometimes is left in the very old processors. So based on this, we consider to combine the two mechanisms together and to make use of the two mechanisms. First, we classified the workload roughly according to the TLB miss rate and the page fault rate. This is the threshold for each of the metric performance metrics, and for a workload it could be quite randomly fall into one of the regions. We analyzed the initialization of the KVM hypervisor, and the following flowchart is presented here. First, this is the user space part of the virtual machine, which is performed by the QEMU context. And this part is the kernel space, which is performed by the KVM, namely in the Linux kernel. So we need to determine the several performance metrics for this for our performance metric sampling. The first, the page fault rate, K2 general page table, and TLB miss rate K2 the nested page table, and the instruction per cycle measures the execution speed of the instructions. And next we worked out algorithm to enable the KVM make the page method determination automatically based on the performance metric data sampled previously. We made it like this. In the shadow table, we observed the page fault rate as the key metric. When the matrix exceeds the average value of the last 10, the average of the last 10 record and the instruction per cycle decreased, we made the decision to transfer to the nested page table. And on the other hand, when in the nested page table, when the TMR exceeds the average value of the 10 last values in history, and the instruction per cycle decreased, we switched into the shadow page table. Now, this is our analysis of the virtual CPU creation, and here there are two possibilities, which is based on the specific kernel variable to initialize the corresponding page method. And our top design is this performance metric read from the hardware performance monitor counter, and then we make the decision for the page model, for the page method. If the page really need page switching, we take actions. If not, we do nothing. Now and we make a detailed analysis to the initialization procedure for the KVM, and we marked the operations in red, and means that they are related with the specific operations on the kernel variable related to the page table, page method switching, and we found that they separated in the whole course of the initialization, and right now I didn't succeed in performing the page method switching in a single week. So we left it as my further work. Now, as our work is very highly experimental, we just test whether the page method mechanical switching works. We modified the Linux kernel part, the source code of the Linux kernel, and also in the QEMU part of in the user space. And we made this test, and later discovered that the output in the syslog, we observed really the dynamic switching, but right now we can only do it by rebuilding the virtual CPU. We can call it a heavy weighted page method switching. Now let's look at the behavior of the workloads, different typical workloads, and in their TLB is read, page fault read, and the instruction per cycle. The red line stands for the TLB is read, and the blue stands for the page fault read, and the blue and the green stand for the instruction per cycle, which is an indicator to the execution speed of the processor. We see different characters of the workload. This is one workload in shadow page table and nested page table. They behaves very differently. And this is another workload, we see that in the shadow page table, there's a very little, there's a very high TLB misread, and in the nested page table, instead there are heavy page fault read. So this is where they suggested that we should apply the nested page table to speed it. And this we should apply the shadow page table to avoid the very high page fault read, to avoid the TLB misread. This is more workload as a general impression. We make a summary. Our contributions gather the TLB misread, page fault read, and the instruction per cycle on the fly from the hardware and the software counters respectively, and design the dynamic page method switching strategy based on the calculation of the 3 performance metric data, and implemented the first heavy-weighted switching mechanism by rebuilding the virtual CPU and memory allocating, but still highly experimental. In future, we will identify the minimum necessary work for a smooth, light-weighted dynamic switching between nested page table and shadow page table, and avoid the concurrency in a multi QEMU with CPU context. As we can also refine the algorithm for determine the proper page method on the fly, which can ensure a wise prediction and avoid a frequent swing between the 2 page methods in certain cases. Then our patch to the Linux kernel and the QEMU will be the 3 made available, and this GitHub. Thank you. Any questions?
Okay, thank you. So any questions? Are there any questions? I know it's tough to be the last speaker of the conference. Actually I have a question. So what do you believe are some of your limitations? And have you thought about how you can, improve on them?
Yeah, I think the limitation is that because my research topic is a little challenging, I failed to make the full implementation of my design, because the limitation, the time is very limited. But in the future, I will continue with this work and work out a better solution for this.
So this website, this GitHub is where you have your
yes,
code.
I will upload
the
source code to this website,
okay.
To make it available and public accessible to other world.
That's good. Yeah. So if you're interested, you can go to the GitHub and you can.
Yeah, I sincerely hope that I can find and other colleagues involved so we can exchange our point of view and make a better work, a cooperation work in this area. And I still have something to see that because in the Big Data conference, I saw most of the papers are dealing with the big data mining techniques, but only my research deal with virtualization, virtual machine technology. But I still find some similarities between them because I also made use of the data analyzing and data sampling metric and to make the right decision for the patient method strategy.